All right, enough people are here. I'm sure other people will come in a little bit later when they realize it's after 12:30, but we are trying to finish up chapter 2 and I want to recap what we did talk about. We talked about basically the idea of the definition of average speed, the definition of average velocity, and then I went as far as letting you know what the average or excuse me, the instantaneous velocity was, and I even made hints as what the instantaneous acceleration would be. I'm trying to see who just came in. Okay, still no James O, no Renee L, no Xavier G, no Jesse with the last name C, and no Charles Ray Atkins. All of these people are ostensibly not here, and I've marked them as absent. If you're not, you need to let me know. But that's what we're working on now. So I had covered this average speed, which is just a different distance traveled divided by time taken. I did have James S. I already had you on there, James. That might have been who I saw a second ago. I'm only missing James with the last name starts with O, Renee with the last name starts with L, Xavier, Jesse with a C on the last name, and Charles Ray with an A on the last name. That's cool. All right, so like I said, the average speed was the total distance traveled divided by the time taken, whereas the average velocity, oh, thank you, Renee. Appreciate that. Whereas the average velocity was the displacement divided by time. So the difference being the displacement is basically the distance you are from home, where you assume you started off at some point in space. We're going to call that point home. It might be the origin, it might not be. The main thing is it's a place in space, so it's has an X, Y, Z coordinate in some sense. And then wherever you're ending the motion, you're going to imagine an arrow drawn from that home to that final position with the arrow on the final position and the tail of the arrow at the home spot. And the length of that arrow, no matter what kind of crazy trip you took, the length of that arrow is the displacement. That's all that matters. And then the average velocity, of course, is displacement divided by time taken. And then if you allow the time interval to get smaller and smaller until the ratio of displacement and time taken gets stable, meaning, you might try it at 1 second apart and you might get 4.57. You try it at half a second, you get 4.68. You try it at three quarters of a second, you get 4.69. You try it at, half a second, you get 3.6. You try it at a quarter second, 3.6. Eighth of a second, 3.6. A 16th of a second, 3.6. You'll see that sort of trend where the 3.6 comes up. Once you've done that, you've basically done the equivalent of taking a limit as delta t approaches zero, and that is the instantaneous velocity. Similarly, you can do that same process with the average acceleration, which is the change in velocity divided by the change in time. So that's the average acceleration, but you can find the instantaneous acceleration by again allowing that time interval to get infinitesimally small or get as small where the ratio of change in velocity divided by time taken stabilizes and stays the same constant. Once you've got it that way on a couple different units of time, whether it be a tenth of a second, a hundredth of a second, or a half second, or a thousandth of a second. Once you've got it small and it repeatedly gives you the exact same number, then you've done the equivalent of taking the limit as delta t approaches zero. And that allows us, in this case, since it's the limit as delta t approaches zero of the change in velocity divided by the time taken, in that case, you get the instantaneous acceleration. So that
Sorry to
just,
interrupt,
go ahead.
uh, but are you meant to be screen sharing right now? Are we
Oh
meant to be
no, not
looking at
yet.
anything? All
No,
right.
not yeah. I've just kind of recap with it. Main thing is I'm getting ready to start an example, and I'll be using these expressions, and I'll probably take the time to write them down then. But I haven't shaved yet. But thank you for that because that is exactly what I occasionally forget to do. So I do appreciate it, anyways. All right, let me go ahead and share my screen now. Now that you asked me, and it's time to do it. All right, it should come up in a second now. I am working from examples in the book, but I'm trying also to change the wording sufficiently so it won't seem like I'm actually copyright violating. So, in this case, I actually kept the same numbers. I just changed the wording around a little bit, but it's not a whole lot different. It says example 2.4, an experimental engine moves along a track, which we assume lies along the x-axis. Treating the engine as a particle, its position as a function of time is x of t equals at squared plus b, where a is 2.1 meters per second and B is 2.80 meters. A, determine the displacement of the engine during the time interval and from T1 equals 3 seconds to T2 equals 5 seconds. Notice I use three sig figs on everything here. B, determine the average velocity during that time interval. And C, determine the instantaneous velocity at t equals 5 seconds. Now, there's a big difference here. In this case, this equation x of t as a t squared plus b, that's a open up parabola. And if you're looking at time intervals starting from t equals 0 seconds to some forward in time, it's never going to go back in position. Like it just keeps going farther and farther away. Whereas if it was a open down parabola and the vertex of the open down parabola was to the right of the t equals 0, then you'd have a portion where the x went high, 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 and then it reached the height of that turnaround spot at the top of the parabola, and then it'd go down, down, down like that. If you have that kind of motion, then you have to do a little bit more to figure out the average velocity because the average velocity is supposed to be the displacement, which is the distance it is away from where it started at. And therefore, if you went through a trip like this, your distance away is only this itty bitty part, whereas you actually traveled whatever distance this was up to that peak and then whatever that distance was down to where you are now. That's the total distance you traveled, and that would be what's used for average speed, but not what's used for average velocity. In this particular case, like I said, they chose at squared plus b such that the graph never runs back on itself except for negative times, and we're only looking at positive times. So these are those words that I told you about that's way more important than the symbols I write on the board and stuff because I'm telling you something big. It makes a big difference. I'll point it out again as we go, but right now let's go ahead and get started with this. So we have an experimental engine moving along a track. It's given a velocity, excuse me, a velocity is given, not a velocity, a position versus time is given as follows. Oops, left off my O there. I left off my I and started writing my O. So we have x of t is equal to at squared plus b, where a is equal to 2.10 meters per second, and b is equal to 2.80 meters. Part A, we want to know the displacement of the engine during the time interval. So what I need to do is make sure, in principle, that I can accurately get the displacement, not the distance traveled. So what do I mean by that? In this case, the graph of AT squared plus BT is pretty straightforward. Basically, we could say this is 1, this is 2, this is 3. So the particle starting roughly here, 2.80 meters. So this is X and it's measured in meters. So it's actually going to start there at t equals 0. And then as time progresses forward, it's going to make a parabola like this. That's what the graph of x of t looks like. The problem is if the graph of x and t maybe looked like this, and you were wanting the displacement, let's say this is 1 second, 2 second, 3 seconds, 4 seconds, 5 seconds. This is time in seconds, and this is x in meters. And let's say this is 1 meter, 2 meters, 3 meters, 4 meters, so on and so forth. If this was the case and you wanted to know the average velocity between t equals 1 second and t equals 4 seconds, what you do is you figure out where the t equals 1 second occurs, which is right there, and the t equal 4 second, which occurs right there, and you might think that since at t equal 4 seconds, it's at the position x equals 2 meters, so you might try to argue that 2 meters is the displacement, but that's not the case. The displacement is how far away you are from home, and home in this case, since we're pretending like we're asking for the average between 1 second and 4 seconds, then the home is the 1 second. At the 1 second, we were at a position roughly 3.5. This is essentially 1.00 comma 3.5, like that. And this one is at 4.00 seconds and 2.00 meters. So you might think it's okay to go ahead and just say 2 meters, but that's not right. We need the distance between the x position at t equal 1 second and the distance between it and t equals 4 seconds. So what we see is delta x in this case. Again, this is an extra one I'm making up. It's not the problem we're working, but I wanted you to understand the words I was giving you. So in this case, delta x is actually supposed to be uh, the total distance, which is 2.00 meters, minus the initial, which is 3.50 meters. Okay, so that's really what you'd have to do in the case of a graph like this one. So when someone gives you an equation, you have to actually know enough about that equation to graph it and to see if it's doing any weird stuff. If it is doing any weird stuff, like where it turns around and goes backwards or the opposite direction it was going, then you have to do it a little differently and analyze it. So again, in this case, the delta x is 2.00 meters minus 3.50 meters, which is negative 1.50 meters. So that would be the delta x that you'd use for the average velocity of that curve. But this was just an example to explain my point. What we're actually doing is this x of t that I have written right here, which is 2.80. I'll leave the units off for a second. T squared, or excuse me, not 2.80. This is a 2.10. 2.10 t squared plus 2.80. That's what x of t is. So for part A, we're asked to determine the displacement of the engine during the interval from t equal 1 second to t equal five, or excuse me, t equals 3 seconds to t equals 5 seconds. So the fact that this graph only goes up, it doesn't have any maxima or minima and then reverses its position. That means all I have to do is subtract the final position from the initial position. So in order for me to calculate the average velocity, which is delta x over delta t, I need the delta x. And remember, delta means change in, and unless otherwise stated, that means x final minus x initial. So x final is supposed to be x of 5.00 seconds, and that gives me 2.10 meters per second times 5.00 seconds squared plus 2.80 meters. And when I do this, I get 5 squared times 2.10. Now I'm going to say plus 2.80, and I get 55.3. Now, technically, the way this works is we're adding and subtracting in this case. So when you add and subtract, there's different sig fig rules than when you multiply or divide. So we're actually, if I multiply the 2.10 times 5 squared, that ends up making 52.5, and they can only have three sig figs, so that actually allows you to one decimal place. And then you're adding that to 2.80. That's the two decimal places, but you're still hindered by the one decimal place that the first multiplication did. So we actually have to write it as 5.3, and any digit after it has to be non-significant. So that's the final exposition. The initial exposition is supposed to be x of 3.00 seconds, which in this case is 2.10. I showed the units last time, so I'm not going to bother showing it this time. So 2.1 times 3 squared plus 2.80, that gives me 21.7 meters for that one. Everybody follow what I did there? Anybody have any
Yes.
questions? Okay, thank you. Appreciate that. If you have any questions, okay, it looks like we're good to go then. All right, I'm just making sure my numbers are what I got. So that is right. Now I can say the average velocity is delta x over delta t, and that average velocity is 50. It's supposed to be final minus initial, so it's 55.3 minus 21.7.
I'm sorry. Are we going straight to B?
Not yet. I'm doing B next. But
Okay,
yeah.
B is average velocity. A is just the displacement.
Okay, thank you. I appreciate that. That was definitely me going off of memory instead of reading my work. So thank you for that. This is A. So what I'll do is I'll write a little A there because clearly I can't be trusted with reading my own problems. So there's A. Therefore, delta X is supposed to be 55.30 meters minus 21.70 meters. Again, those are not sig figs. So I'll say 55.3 minus 21.7, and that gives me 33.6 meters. So that's the displacement. And notice we did do our check to make sure that there wasn't a minima or a maxima in between. If there's a minima, maxima, or possibly even a point of inflection could cause some issues. But if it's any of those in the interval that you're studying, then you have to do some manual labor to figure out what the displacement is, other than just taking the difference in coordinates. All right, now part B, it says determine the average velocity during the time interval. So that's where I'm going to do what I was starting to do earlier, but thankfully a good student was paying attention and caught me before I screwed up. V bar is equal to delta x over delta t, and that gives me 33.60 meters. Notice I'm carrying an extra sig fig. That's what you're supposed to do with intermediate calculations. Now the time interval from 3 seconds to 5 seconds is 2.00 seconds. So we should be able to get three sig figs out of this. So when I divide 33.6 by 2, I get 16.8. And that turns out to be meters per second is equal to V bar. So that's our second answer. Now, the third answer is determine the magnitude of the instantaneous velocity at t equal 5 seconds. In this case, what we're going to do is V instantaneous, which is also what I'd call V of t, is equal to dx over dt, which is d by dt of at squared plus b, which is clearly 2at. And of course, we then evaluate that at t equal 5 seconds to figure out what the velocity actually is, the instantaneous velocity. So v of 5.00 seconds is equal to 2 times 2.10 meters per second times 5 seconds. And that, of course, gives me an average velocity of 21 meters per second. Anybody have any questions on that? All right, so that part I explained, that's probably the most important part because that's what's going to trip you up when you go to just do delta x is, x final minus x initial. Uh, if the thing is really participating in one-dimensional motion, that could possibly not be a problem. But if it's actually in two dimensions, it very much is probably a problem. So just remember, you've always got to look at the position versus time graph to see if there's any maxima or minima, because what matters in the average velocity is the displacement, and that's the distance from the initial point to the final point of whatever motion you're studying. All right, I want to move on, assuming no one has any questions. Now we're moving on to another example. This example is again just like in the book. If a car accelerates from rest to 90 kph in 5 seconds, uh, I'm going to assume both of those are 2 sig figs, by the way, even though I prefer to make them 3 sig figs. So if a car accelerates from rest to 90 kilometers per hour in 5 seconds, what's the magnitude of its acceleration? So in this case, we're actually talking about average acceleration. So I've got another equation I'm going to give you guys. So for starters, I have the initial velocity. This is part of what you're learning in physics. When you learn physics, I told you one of the things you're doing is you're learning certain symbols correspond to certain values. For instance, 5.0 is a time, so you'd label that a t. 90 kilometers per hour is a velocity, so you'd label that as a v. It's actually a speed because they didn't give you a direction, but we haven't learned about that yet. So it could be speed or velocity at this point. I'm just calling it v because there really is a lot of similarities between velocity and speed. A lot of times, not all the time, a lot of times the velocity or the speed is just the magnitude of the velocity, but that's not always the case, especially when you're talking about average speed versus average velocity. As I told you in class, if you took off from home plate and ran to first, then to second, then to third, and then touched home plate, and then you wanted to calculate your average speed, if you were playing on a Major League Baseball field, if I remember correctly, the bases are 90 feet in that case, so it'd be 4 times 90, it'd be 360 feet divided by however much time it took you to run it. That would be the average speed. Whereas the average velocity would literally be zero because you took off from standing on home plate and then you ended back up standing on home plate, so your displacement was zero. All right, so V is equal to 90 kph. And what I'm going to do is go ahead and put that over 1 hour because, like I told you, when you convert units, which we're going to need to do here, it's important that you normally make sure the first number is a fraction so you don't get confused as to whether it's a denominator or a numerator. In this case, what we're going to do is we're going to convert this to meters per second. So what we're going to do is take 1 kilometer, put that in the bottom, and of course 1 kilometer is equal to 1,000 meters, so that'll actually convert it from kilometers per hour to meters per hour. And then we're also going to take and multiply it by 1 hour on the top and 3,600 seconds on the bottom. In this case, that shows us that the hour cancels out in the top and bottom, and it gives us our actual velocity in meters per second. Notice the equivalent is basically us dividing by 3.6. So that's a common thing that you're going to do in converting kilometers per hour to meters per second. You're just going to divide by 3.6. So in this case, I get 90 divided by 3.6 is about 25.0 meters per second, and that's technically the final velocity. And remember, I was telling you, you've got to be able to figure out symbols for quantities. You also have to infer certain quantities. Like I use the word rest, which meant if a car accelerates from rest, that is code for, hey, your initial velocity is zero. So I'm also going to write down v initial is equal to 0 meters per second. And I'm going to use the equation that the average acceleration is the change in velocity per unit time. It's the rate of change of velocity that really is the acceleration. So I can take this change in velocity, which is final minus initial, divided by the time taken. In the case of final minus initial, that's going to be 25.0 meters per second minus 0 meters per second divided by however long it take, oh, 5 seconds, sorry, however long it takes to make the trip, which was 5 seconds. And obviously 25 divided by 5 is just 5.00 meters per second every second. So that is your average acceleration. And notice how I'm saying it as meters per second per second. Again, that's a way of you better understanding, hopefully better understanding acceleration and how it differs from velocity. Acceleration has a meter per second in it, but it's meters per second, whereas velocity is just meters per second. Okay. And in principle, if this was a true constant acceleration, which generally cars do not have constant acceleration for any appreciable time. So if this really did have a uniform acceleration where, at 2.5 seconds, it was exactly 50% of 90 kilometers per hour. And if at half of 2.5 seconds, it was one fourth of 90 kilometers per hour. If that was really the case, then that would be a nice uniform acceleration and a constant acceleration. But in this case, it's not necessarily. All we're doing is calculating the average. Anybody have any questions on that? Okay, conceptual example. Does the velocity of a of hmm, does the velocity of an object being equal to zero mean that its acceleration is zero? So does the velocity of an object being equal to zero mean that its acceleration is zero? Anybody have any ideas on what that answer might be? You
No,
may
it
chat.
does not.
Exactly. It does not at all. In fact, you can have at the top of motion, for instance, when I throw this pin up, when it reaches the top of its motion, it actually comes to a stop and then it starts accelerating back downward. But oddly enough, the acceleration, the instant it leaves my hand, all the way to going up the top and then all the way down to me catching it, the acceleration during that period of time is always 9.8 meters per second every second downward. That's the acceleration due to gravity that we'll learn in a few minutes. But that's basically a constant acceleration. And you can see that even though the velocity was zero, it was still accelerating. Now, if the velocity is zero and then you wait, a tenth of a second and it's still zero, and you wait another tenth of a second and it's still zero, then yes, the acceleration is zero. Okay, but not just at any instant. The second part of the question is, does the acceleration being zero mean that the velocity is zero? And that's also not true. Yes, you can, for instance, be traveling down the road at 60 miles per hour, using gas, by the way, because you're fighting friction forces and all that good stuff. But still, if you're traveling at a constant 60 miles per hour and not changing directions, or even the steepness of the curve, or the steepness of a down drop or whatever, then the acceleration can still be zero. In fact, there's a whole branch of mechanics called statics, and there's actually a course that you take in engineering called statics, and that is the study of objects that aren't accelerating. It seems like it's studying objects that aren't moving, because a lot of stuff you'll do is design trusses to put on houses or bridge trusses and stuff like that, which obviously are not moving, but it's exactly the same calculation if you wanted to do that for a system that was moving at a constant speed. So just keep that in mind. Any questions on that? All right. Let's look at example 2.7 now. Now this is one of those cases where again I told you it's better if you have your book. I'm going to read the example. I didn't have time to type this one up or any other ones, so I'm going to read the example and then you guys can uh, ask me if you don't remember some part. It says car slowing down. An automobile is moving to the right along a straight highway, which we choose to be the positive x-axis. The driver puts on the brakes. The initial velocity when the driver hits the brakes is v1 equals 15 meters per second, and it takes 5.0 seconds to slow down to v2 equals 5 meters per second. What is the car's average acceleration? So this, as I said, is example 2-7. I've been using dots instead of dashes. But what we've learned is that V1 is equal to 15.0 meters per second. V2. Now, you'll notice me drawing that V kind of funny that I'm drawing it like the Greek letter nu, NU. That's really a lot of times what we're using for the symbol for velocity. So if you see me write it that way, that's all because I'm in principle, there might come up another V sometime later. The V2 is only 5.00 meters per second. Actually, they only gave me 1 0. So I'm going to underline the second one. And the delta T in this case was the 5.0 seconds. And again, I put an extra digit on there and underlined it so everybody knows it's not a sig fig. So the average acceleration is delta V over delta T, and that means final minus initial. The final is 5.00 meters per second minus 15.0 meters per second, and all this will be divided by 5.0 seconds. Now 5 minus 15 is negative 10, so that gives me negative 10.0 meters per second divided by 5.0 seconds. So finally you get a negative 2.0 meters per second. And that's our average acceleration. Notice this is a case where we actually were slowing down and we were going in the positive direction. So this is a normal case where someone say, "Oh, look, the negative acceleration, that means it's decelerating." And yes, it does, but it's not that way. That's not the general rule. For instance, if I did V1 is equal to actually, let's do it this way. Let's do an average velocity. Yeah, I'll do an average velocity. Let's say the velocity initially V1 is negative 5.00 meters per second. The negative just means it's moving in the negative x direction. Now I'm speeding up while going in the negative x direction. So V2 is going to be negative, let's say 15.0 meters per second. And let's say the delta t was again 5.00 seconds. So I'm going to call this a counter example. Ooh, I don't even know what happened to my brain just then. So the average acceleration in this case is negative 15.0 meters per second, which is markedly faster than the initial velocity, which was negative 5.00 meters per second. So it's obvious the thing is actually speeding up. But this time I've got negative 15 minus negative 5, which basically becomes negative 15 plus 5, and therefore we get negative 10.0 meters per second divided by 5.00 seconds, which gives us 2.00 meters per second equals A average. So in this case, you see that we sped up and got a negative acceleration. So that's what I mean. If you're actually speeding up but going in the negative direction, that will come out to be a negative acceleration, and that is what we normally associate with accelerating, not decelerating. Any questions on that? All right. Now the next step is basically just providing you with some more equations. So far we've got the average speed is distance traveled divided by time taken. Okay. The average velocity is displacement divided by time taken. Okay, which we can write as delta x over delta t, but you got to remember those warnings that I gave you that if a graph goes up and down, you got to be careful. You can't just necessarily subtract x2 minus x1, especially if it's in two dimensions. And we then found that the instantaneous velocity, which we might also write as v of t, is equal to the limit as delta t approaches 0 of delta x over delta t, which you all should recognize that as dv dt. So another equation we came up with was the average acceleration is the change in velocity divided by the time taken. And we can say A of t, or I should say A instantaneous, which is A of t, is equal to the limit as delta t approaches 0 of delta v over delta t. And that, of course, is dv dt, but it's also d2x over dt squared. And that's A of t, our instantaneous acceleration. Okay, so these are the equations that we've used so far and that I've introduced you to. I actually haven't used the derivative one but once so far, but now we have to actually figure out some way to get us other equations to use. So if I assume A equals a constant and V equals V0 at t equals 0.0 seconds, and x is equal to x0 at t equals 0.0 seconds, then we can say A, which equals a constant, is equal to dv dt. What I'm going to do is take that constant A and take the dv dt that's on the other side, and I'm going to multiply both of them by dt. So I'm going to get A times dt, and remember A is a constant, and I'm going to get dv dt times dt. Now I've multiplied both sides by dt, and as long as dt wasn't 0, I've done nothing wrong. You're allowed to do to one side of equation whatever you do to the other side, as long as you do them both. The only thing you can't do is divide by 0 or multiply through by 0, even accidentally. Since the a is a constant, the next step I'm going to do is I'm going to integrate the whole equation on both sides, but I'm going to leave the a out in front just to remind you that it is a constant and I didn't really have to integrate that. So when I integrate this, I have to add a constant is one way of looking at it because we're integrating without a limit of integration. So for that case, we could in principle have a constant on the left hand side and then another constant on the right hand side, but I could pull them all to one side and make a new constant and then it'd just be one. So that's what I'm going to pretend like was done. When I integrate a dt, I'm just going to get a times t. Uh, And then when I integrate dv/dt, that's the fundamental theorem of calculus. The fundamental theorem of calculus says a derivative undoes integrals and integrals undoes derivatives. So if I'm integrating the derivative, I just get back the original function, which in this case is just plain v, and I'm going to put the integration constant there. I'm just going to call it c. There is another way of doing it. You could have taken the integral on the left from t equals 0 to t equal t, and then you'd take the integral on the right hand side from v equals v0 to v of t. Mathematicians don't really like that kind of thing, letting the limit of integration be a function. But anyways, that's what way we do it. So now, if I remember, I can actually say, oh, this v must be my v of t I'm looking for. So I'd say v of t is equal to at minus this constant c. And what I want to do is v of 0 is supposed to equal v0. So that means v0 is equal to a times 0 minus c. And that means that the v0 must be equal to negative c. So we now can say v of t is equal to v0 plus a t. That's one of our results. In fact, that happens to be the same thing as the average acceleration, uh, which could be written v minus v0 over t instead of v minus v0 over delta t. So you can see it's really the same equation as the average velocity formula, but we just derived it. Now I'm going to use the fact that v of t is actually dx over dt, and I'm going to go ahead and integrate that. So instead of v of t, I'm going to have v0 plus at. I'm multiplying both sides by dt and integrating. Again, I'm going to integrate using the integration constant, but I'm only going to make one of them. So the right hand side or the left hand side is going to become v0t plus 1 half at squared is equal to x of t plus a new constant. Therefore, we can say x of t is equal to 1 half at squared plus v0t minus a constant. But x of 0 is supposed to equal x0, and that would be, of course, 0 plus 0 minus c. So now we can say that x is equal to, and notice I left off the x of t. I can do that up here as well. Just call that v, and then it looks more like an equation that we can use for kinematics. So the same thing's happening here. I now have x is equal to 1 half at squared plus v0t. And then, of course, the minus c becomes plus x0, and that is our new kinematic equation. So with these equations that I started off with in the red boxes here, I was able to generate one equation we already had, the top purple one, and then I was able to generate a new equation which we didn't have. Now, what I'm going to do is take this equation, let's call this one 1, and let's call this one 2. Let's solve 1 for t and plug that t into equation 2. So when I do that, I'm going to get x is equal to 1/2 times A times T. When I solve this for T, I get V minus V0 over A. That quantity is going to be squared plus V0 times V minus V0 over A plus X0. So what I'm going to go ahead and do is subtract X0 from both sides. And now I'm going to go ahead and start distributing this stuff. I'm going to get X minus X0 is equal to A over 2 times V squared minus 2V V0 plus V0 squared, all that divided by A. Okay, and you can see that that A there is going to cancel out with this A. Now I'm also going to distribute the V0 in this second term, so it's going to become V0 minus V0 squared, all of that over A. Uh, I think that's, oh, this A down here is squared, by the way. I forgot to square it because the time was actually squared. So now you see that that's going to cancel out that. And what we get instead is I can go ahead and multiply through by 2 on this fraction to the right. I'm going to multiply by 2 top and bottom. And then what I have is one common denominator that is 2A at the bottom. And by doing that, I have v squared from the first term minus 2v v0 from the first term plus v0 squared from the first term. Now, in order for me to take that second fraction, I got to multiply through by 2. So that's going to be plus 2v v0 minus 2v0 squared. Now what you can see is the 2v0 cancels out with the negative 2v0, and the v0 squared actually combine to give us negative v0 squared. So now I can say that x minus x0 is actually equal to v squared minus v0 squared over 2a, and this is it. This is what I normally, the way I normally write this equation. V squared is equal to V0 squared plus 2 times A times X minus X0. That is our final, well, not our final. I'm going to show you another one as well. But that's one of our main kinematic equations that we use. We'll call it 3. Another one we can use in principle is this one that's only a true. These two expressions, actually all 3 that I just derived, were based on the acceleration being a constant. So if we stick with the acceleration being a constant, we can come up with another equation. And this one sort of you can figure out from common sense, but basically it just says the average velocity is v0 plus v1 over 2. And again, that is only true in the event that the acceleration is a constant. Uh, Not all calculus-based physics classes even include that 4, and there's a lot of calculus-based physics classes and some algebra-based physics classes where they don't even allow you to use equation 3. So you don't necessarily have to have it, but it does come in handy. So those are our kinematic equations. That's what we're going to make use of. Let's look at example 20 or 2-8. So this is another one from the book. So 2-8 says a particle is moving in a straight line so that its position is given by the relation x is equal to 2.10. This says the same units as it did before, t squared plus 2.80. So the 2.10, you recognize that from a previous example that had units of meters per second. And the 2.80, you also recognize that had units of meters. And what they want us to calculate is A, they want the average acceleration from 3 to 5 seconds. To 5.000 seconds. So that's what they want in part A. calculate its average acceleration during the time interval from t1 equals 3.00 seconds to t2 equals 5.00 seconds, and then B, its instantaneous acceleration as a function of time. So that's what they're wanting us to calculate as well. So this is not using one of the kinematic equations, but this is using what we learned about derivatives and stuff of that sort. So first off, for part A, we're trying to calculate the average A. The average A is supposed to be V minus V0 over T, or delta T if you want it. And remember, it's just final minus initial. So having the zero is another version of initial. It's a subscript zero, meaning at time T equals zero. And having no subscript means that's the last one. Okay, so we're okay in using that. But in order to make sense of it, I've got to compute what the velocities are. So first off, I'm going to take dx over dt, which is actually v of t. And that's going to be, of course, 4.20 t. That's the actual velocity as a function of time. So now I can say V is equal to 4.20. Remember, the units are meters per second, times, in this case, it's the final one. So I'm going to say 5.00 seconds. And 5 times 4 is 20. 5 times zero point 0.2 is 1. So this is the 21.0 meters per second that we found earlier. Now I need to find the V0, which is equal to 4.20 times 3.00 seconds. 3 times 4 is 12. 3 times zero point 0.2 is zero point 0.6, so this would be 12.6 meters per second is V0. So I can now say A bar, which equals delta V over delta T, is actually equal to 21.0 meters per second minus 12.6 meters per second divided by the time interval between 3 seconds and 5 seconds is 2 seconds. So now all I'm going to do is not trusting my brain, just I'm going to take 21 minus 12.6. I'm going to use my calculator on that. Didn't need to, but just keeps me from making a boo-boo when I'm talking while working. So this turns out to be a change in velocity of 8.4 meters per second and divided by 2.00 seconds. That only allows us basically 2 sig figs. So divide that by 2 and we get 4.20 meters per second is the average acceleration over this time interval. Now for part B, they want to know the instantaneous acceleration. Well, we found out that in part B, or in part A, we found out that V of t is actually equal to 4.20 t. And we know that A of t is equal to dV of t over dt. So if I take the derivative of this V of t with respect to time, I just get 4.20. And then it's important for me to remember that those units are meters per second every second, and that's A of t. So this is in fact a case where the acceleration is a constant. Anybody have any questions on that one? All right, there is a conceptual example. It says figure 219 shows the velocity as a function of time for two cars accelerating from 0 to 100 kilometers per hour in a time of 10 seconds. Compare for the two cars A, the average acceleration. So if you're looking at this graph, let me give you a rough drawing in case you don't have your
I
book.
I do have a quick question.
Yeah, what's that?
For part A,
Mm-hmm.
the 4.20 is
Mm-hmm.
just the derivative of the 2.1 t squared. You just didn't write
Exactly.
it out.
Yeah, yeah.
Okay, just making sure.
Yep, yeah. I wrote it up here, but you might not have noticed it. So the 2.9, it says the average acceleration. So what I'm going to do is draw this graph real quick. And basically the graph looks like this. This is the t in seconds. and this is v in actually this is v in kilometers per hour. And what we have here is one vehicle that does this and another vehicle that does this. And actually, I should bring them a little closer together. Let's take both of those out. So this is the 10.0 seconds mark. And this is the 100 kilometers per hour mark. So that's the two velocities. This is car A and this is car B. And for part A, they didn't want to know, compare the two cars' average acceleration. Well, the acceleration is the change in velocity per unit time. So if we took, for instance, our time interval to be from here to here, then the acceleration for this one would be this slope, but the acceleration for this one would be this slope. And it's not easy to tell, but I think you can tell that the acceleration of the high of A looks like it could be in principle a little bit higher, but it could be if you're talking about the whole motion. And actually, let's see. Okay, so they're actually wanting the average acceleration for the whole time interval, not for the little time interval. I'm glad I went back and read that. I hadn't worked this since last week. But yeah, in this case, since we're going the whole time interval, the average velocity is the slope of the secant line, and the secant line is the same for both of them. It's a line that starts at t equals 0, which is the origin, and ends at the end. So for part A sub A average is equal to A sub B average. Now for part B, it says compare the instantaneous acceleration. And in this case, we're talking about instantaneous acceleration at any point. Since this is a velocity curve, the slope is really the acceleration. So for instance, you could take this dot right here and draw a line that's tangent to it, which is a lot harder to do than you might think. But there's the tangent to that one, whereas the tangent here is this line. So in this case, it looks like at least at this early time interval, the acceleration was larger for car A than it was for car B, at least at that initial point. When you go down here a little further, let's say this point and this point right above it, so these are the same points in time, if you would, then you're going to see that the average acceleration here is that line, and the average acceleration here is this line. So, and at the early seconds, A has a larger acceleration, but in the later seconds, closer to 10, B has the larger acceleration. And then for part C, it says compare the total distance traveled. In this case, we can think about the equations, and the average acceleration is the same. So we have basically V0 is equal to the average acceleration times the time taken. So that means the final velocity obviously would be uh, dependent on the initial velocity plus AT, but you could also figure out that the lost what I was doing. The distance traveled is given by a kinematic equation like x is equal to 1/2 at squared plus v0t plus x0. And you can always set the x0 to 0, pretending like basically the object started from the origin. That's always acceptable. But in this case, you can see they both took the same amount of time to get up to the final velocity. They both had the initial velocity equals 0. We can make this equal to 0 by choice. And since they took the same amount of time, but their average accelerations were the same, then in principle, the distance should be essentially the same. That would be what you did on average. But as you might notice, the velocity of the A vehicle gets it going a lot quicker distance, because really, to be honest with you, remember the distance traveled is x is equal to dv dt, or another way of putting that is x is equal to the integral of velocity with respect to time. So the area under the curve shows you that part of car A actually has a larger area. Therefore, the total distance traveled by car A should be larger than the total distance traveled by car B. And that's just from your understanding that, oh, wait, I've got a velocity versus time graph. And in order to actually find out what the distance versus time is, I've got to integrate that. And then you see, oh, well, integration means the integral of v dt, and lo and behold, that's exactly the area under the curve. And then you can see the area under the curve for car A is bigger than the area under the curve for car B. So in total, car A uh, travels a larger distance in that period of time. Any questions on that? All right, so I need to show you one free fall type problem, and I did more or less a derivation, but you should look at example 211 and 210. Those are all things you should be able to do. They're pretty easy, but you can also look at my videos that I did. So I've done a lot of examples on these kinematics, both in week 2 as well as week 3. But I want to show you another type of problem as well. And in this case, let's say the police officer and the speeder was a good one. But for free falling objects, that's where I'm going for an example for. So let's look at example 215. Now, example 215 says, suppose that a ball is dropped from a tower. That's one of those things you're supposed to infer that it was dropped and therefore the initial velocity was zero. So suppose that a ball is dropped from a tower. How far will it have fallen after a time of t equal 1 second, t equal 2 seconds, and t equal 3 seconds? So V0 is equal to 0. What we want is V of 1.00 seconds is question mark. V of 2.00 seconds is question mark. V of 3.00 seconds is question mark. So what we have here is an expression that we can use, a kinematic expression that we can use. And what we need is velocity. So we want to know an equation that has velocity in it. We want to know an equation that has time in it. And we want to know an equation that has an initial velocity in it. And that gives me ultimately the distance traveled. So I'm looking for an equation that has initial velocity, the acceleration, which we know is 9.8 in the downward direction, and so on and so forth. I think you all can recognize that this equation fits the bill. I'm going to go ahead and assign x0 equal to 0, but the fact that it started from rest came from the problem. So ultimately we say x, uh, wait a second, did it ask for the velocity or did it ask for distance too? Yeah, I don't know why I wrote that they were asking for velocities. They were actually asking for distances as a function of time. So I'm not really sure why I wrote that, but I'm glad I caught it before I solved the problem. So it's x of those. So I'm going to go ahead and use this. And what we're going to use is 1/2 at squared because the other two terms are 0. So I'm still trying to write v, x1 is equal to x of 1.00 seconds is equal to 1/2. Now I'm choosing to draw downward as the positive direction so that I won't have a negative sign. You're free to do that at any point. So I'm calling the acceleration positive 9.80 meters per second every second. and then I'm multiplying that by 1.00 seconds squared. So half of 9.8 is 4.9. So this one turns out to be x of 1.00 seconds is equal to 4.90 meters. So there's one of our answers. Now, another thing you can see here is x is proportional to t squared. Conceptually, what that means is if the time goes up by a factor of 2, then the distance goes up by a factor of 2 squared, which equals 4. So 4 times 4 is 16. 4 times zero point 0.9 is 3.6. So this should be 19.6. That's one way you can do it. So this gives me 19.6 meters. But you could also do it this way. I'll actually write it in red so you can see what's happening. But it's 1/2 times 9.80 times 2.00 second. Oh, I don't need the second. I didn't put it in the other part. Times that, and you'll get it as well. But I just used the principle of what a square means. Okay, so an exponent of 2 means a square, and since x is directly proportional to it, which it wouldn't be if it was if it had an initial velocity that wasn't 0, but this one did have an initial velocity that was 0, so, or that was 0, so that's okay. All right, so there's our answer for the second part, and then the third part was x of 3.00 seconds. Now, when t goes up by a factor of 3, then x goes up by a factor of 3 squared, which is 9. So really the answer is going to be 9 times 4.90. 9 times 4 is 36. 9 times zero point 0.9 is 81. So this should be 44.1. But again, you can actually use the formula as well by saying x is equal to 1/2 of 9.80 times 3.00 squared. When I punch that in my calculator, zero point 0.5 times 9.8 times 3 squared, that gives me 44.1 as well. Okay? Any questions on that? Example 216. We only got like 8 minutes left, so example 216 says thrown down from a tower. Suppose the ball in example 215 is thrown downward with an initial velocity of 3.00 meters per second. I'm going to still call downward the positive direction, but now I say V0 is equal to positive 3.00 meters per second. And what they want to know is what's the position after 1 second. So A, they want to know x of 1.00 seconds is equal to question mark. And then B, what would be its speed after 1 and 2 seconds? So that's what we're trying to figure out. My solution is going to involve certain equations. Obviously, I want to do x equals 1/2 at squared plus v0t plus x0, but I'm going to fix x0 to be 0. I'm also going to use, since they want to know the speed, which is in most cases the magnitude of the velocity, I can use v final equals v0 plus at as another equation for part B. So for part A, x of 1.00 seconds is going to be 1/2 times 9.80. Y'all seen how the units work out, so I'm not doing that again. Plus 3.00 meters per second for that one times 1.00. So the initial position, or excuse me, the initial term is the same as what we had before, 1.8, 9.8 times 1/2 times 1 is 4.90 meters. And then I'm adding 3 meters to that because that's what it has just as a result of the initial velocity traveling at 3 meters per second, basically. So with that in mind, we're going to say instead of 4.9, we're now going to have 7.9 meters is the distance of 1 second after 1 second. Now for part B, they want to know the velocity, or actually they want to know speed, but that's the same thing when we're talking about magnitudes. So this is going to be 3.00. I haven't used this equation yet with the units, not in this way. So 9.80 meters per second per second. So I'm showing the units now. And this is 1.00 seconds. So 1 times 9.8 is going to give me 9.8. Then I'm adding 3 to that. That's going to give me 10, 11, 12.8 meters per second is equal to V of, or excuse me, is equal to V of 1.00 seconds. Now to find V of 2, or excuse me, V of 3, yeah, 2 seconds is what it was. We do the same equation, but we can't do the little trick we did before because when the initial velocity is zero, is not zero, it's not directly proportional. And in this case, it's just proportional to t, not t squared. So in this case, it's still going to be 3.00, not including the units this time, 9.80 times 2.0. 2 times 9.8 is 19.6. 19.6 plus 3 is 20, 21, 22.6 meters per second equals V of 2.00 seconds, which is also, like I said, the speed. So the speed at 1 second is 12.8 meters per second, and the speed at 2 seconds is 22.6. And that's basically it. All right. Uh, You guys are free to go when the time runs out. I'm going to do another quick derivation and show you how you use that stuff we did for the derivation. If someone gives you A of t is equal to 3t plus 4, I could ask you that question and assume V of 0 is equal to 1.00 meters per second and assume that uh, x of 0 is 0.00 meters. If I assume that, I can figure out what x of t is and what v of t is, and that's what I'm doing now. So this is a sort of derivation, but it's the type of problem you're supposed to be able to do. So I'm going to say a equals dv dt gives me 3t plus 4 is equal to dv dt. I'm going to multiply both sides by dt, and then I'm going to integrate both sides. This time I'm not going to use the integration constant. I'm integrating with respect to t on the left-hand side, so I'm going to say this is from t0 equals 0 to some final time t, and this is going to be from v equals v0, which is 1.00 meters per second, to v of t. When I integrate the left-hand side, this becomes 3/2 t squared plus 4t is equal to, now I'm going to get v of t minus 1.00 meters per second. So I now know that the velocity as a function of time is equal to 3/2 t squared plus 4t plus 1.00, and obviously the number 3/2 has to have units of meters per second cubed because it has to come out in meters per second for the velocity, and you have to multiply that 3/2 times second squared, so it has to be meters per second cubed. So that's the units of this quantity. That's meters per second cubed. The units for this quantity, 4, has to be meters per second squared because it's got to be multiplied by a second and give a second. And the unit for this one, of course, is just meters per second. So we now have the velocity as a function of time, but velocity as a function of time is also equal to dx dt. So I'm going to integrate that too. So now I'm going to say 3 halves t squared plus 4t plus 1.00 is equal to dx dt, multiplying both sides by dt, and then integrating t 0 equals 0 to t. This time I'm integrating from x equals x0 to x of t. And of course, x0 was 0.00 meters. So now when I integrate this, I've got x of t minus, this is the right hand side, minus 0.00 meters. So this came from the right hand side. And then the left hand side is going to be 1 half t cubed plus 2t squared plus 1.00 t. And that means x of t is equal to 1 half t cubed plus 2t squared plus 1t plus 0. And again, the units you can work out on your own, but that's what you do if you're giving an acceleration that's a function of time and you're asked to find the position as a function of time. You guys, of course, free to go. I ran about a minute over. And thank you for coming, and I will see you guys on Wednesday. We are finished with the lecture of chapter 2. There's a lot more examples you can see, but I think I've done a pretty good swath here. Thanks for coming, everybody.
All right. How soon can we expect the video to be uploaded to YouTube?
This video, I actually might be able to do it in about 10 minutes. If not, it should probably be up by 4:30.
All right. Very nice. Thank you.
All right. See you,
All
Liam.
right. Enjoy the rest of your day. See you Wednesday.
You too. Thank you, sir.
No.
Anybody else have any questions? Zach or Monty, you have any questions? All right. I'm going to go ahead and call it a day then. I'm going to stop sharing. Thanks again, everyone. Have a good day. See you Wednesday. Don't forget to do your homework. We're finished with chapter 2.